Welcome to part 4 of this week's online lecture. In part 4 we will continue our discussion of analysis by infrared techniques. Let's have a look at the structural analysis of an unknown sample. And this is where we're going to become a little bit more applied. We've done all the principles for rotational and vibrational spectroscopy, but it does have a variety of applications beyond what is purely theoretical. If we compare the infrared absorption frequencies of an unknown with those of known molecules, we can frequently identify functional groups that are present in the molecule. We could potentially identify the molecule itself with its characteristic infrared spectrum. All of the stuff we've been doing so far is called normal mode analysis. But it is possible that bends and stretches can couple together, that they can excite each other, and that they are not truly separated as is suggested in a normal mode analysis. So in a real molecule, because of the anharmonicity that is present, the separation isn't perfect, and so they get coupled together. So we're going to get two classes of vibrational bands arising. One is known as the skeletal vibrations, and the other is known as group vibrations. So let's have a look at these two classes of vibrational bands. First of all, let's talk about the skeletal vibrations. And these are normal modes that involve strong coupling between stretching or bending motions of atoms in a linear molecule, a branched chain structure in a molecule, or a ring system. And it is usually not possible to assign a particular stretch or bend due to the coupling that is present. The reason why you're getting this coupling is essentially because the force constants, say, for the CC bonds are all roughly the same. So they all have a tendency to couple together quite strongly, both in terms of stretching and bending. And they also involve the same reduced masses, so these bending or stretching couple together to give what is known as the fingerprint region of the infrared spectrum. The second class of vibrations is probably a little bit more familiar to you in terms of identifying molecules. It is what is known as group vibrations. These are modes that are localized within certain regions of the molecule. For instance, here we've got a methanol molecule with an OH stretch which is localized. You would undoubtedly have seen the OH stretch being present in the spectrum of alcohols. And the reason why is that the force constant and the localized reduced mass of the OH system is significantly different from the force constant associated with all the other bonds in the molecule, say the CO or the CH bonds. And because it is so significantly different, it can't really couple with those other bonds in order to form a normal mode which expresses itself over the entire molecule, as we discussed for skeletal vibrations. So although this cannot really occur in complete isolation, largely it does. The largest amplitude of any normal mode of the OH stretch will be pretty much the motion of the oxygen and hydrogen atoms. There will be a little bit of association with the motion of the carbon and hydrogen atoms, but it is so small that we can consider it to be virtually separate. And this is what we call a group vibration. And it is generally occurring when the force constants or reduced masses are significantly different from those of the surrounding atoms or groups. So what might be the justification of this? Let's consider some XH stretches where X could be a carbon, nitrogen or oxygen atom, say. Now if we wanted to write down what the vibrational frequency for an XH stretch would be, we can write it out in terms of Hooke's law. It will be equal to 1 over 2 pi times the square root of the force constant of the XH stretch over the reduced mass of the system. However, the reduced mass of the XH group is going to be close to the mass of the hydrogen atom. We can reconcile this by considering the reduced mass more closely. Remember that the reduced mass of XH is the mass of X times the mass of H over mass of X plus mass of H. Now notice that the mass of X is greater, perhaps much greater than the mass of hydrogen. The mass of hydrogen being the smallest possible relative atomic mass. What does that mean? Well, it means that I can say that the denominator of the reduced mass is approximately equal to the mass of x, which will mean that the mass of x will cancel with the mass of x on the numerator, and then we will be left with a pseudo-diatomic limit for the reduced mass, which will be equal simply to the mass of the hydrogen atom. This is what we mean by the pseudo-diatomic limit. So if we look at OH stretches, they occur at approximately 3,600 wave numbers. And using this kind of analysis, that must correspond to a force constant of about 770 newtons per meter. Similar considerations apply to NH and CH stretches. We would expect to see them occurring at around 3,000 wave numbers. And that kind of frequency is much higher than the kind of frequencies associated with, say, a OC bond or a CC bond. And so because of the large difference in the frequencies, it is not surprising that we can treat group vibrations separately. From a classical analysis, if we couple springs together and the springs have different force constants, what you would find is that if you try to excite that coupled spring system, say at the resonant frequency of one of the springs, then you'll see the stretching at quite large amplitudes for that particular spring, but virtually nothing happens to the other spring. And that is essentially what is going on here. Similarly, we can consider a carbonyl bond, and that is a particular group vibration you can identify very easily in an infrared spectrum. This forms a group vibration because it will have a significantly different frequency from the surrounding system, not least because the other bonds that are nearby are usually single bonds, which are going to have much smaller force constants. Similarly, if we look at the vibrations involving halogens, and say we go from fluorine to bromine, because their atomic mass is increasing, they tend to also greatly increase their reduced masses, and therefore the vibrations are going to be at much different frequencies and can largely be treated as vibrating independently from the rest of the molecule. So let's have a look at the trends that might occur in these kinds of stretching vibrations. This is the equation for the frequency of a vibration according to Hooke's law. Let's look at increasing bond order, for instance. So X can be either carbon or nitrogen. How does the frequency change as we increase the bond order from single bond to double bond and to triple bond? You can see that the vibrational frequency is increasing as you increase the bond order. This makes sense because we know that increasing the bond order increases the force constant of that bond, and the vibrational frequency is proportional to the square root of the force constant. What about as we go down the group? When we go down a group, we are increasing the reduced mass because the atomic mass of, say, the halogen is increasing. So indeed, a CF stretch is seen to occur somewhere between 1,000 and 1,400 wave numbers, whereas a CL stretch is somewhere between 600 and 800 wave numbers, and a CBR and CI occur at below some 667 wave numbers. Eventually, this kind of behavior is tailing off, and that is because as we increase the mass of the halogen, in comparison the carbon is becoming really quite light, and we are approaching the pseudo-diatomic limit for this system. If we went from iodine to astatine, it wouldn't make much difference because the reduced mass of the system is really just the mass of the carbon atom, so it kind of asymptotes to that kind of frequency. Well, this is the end of part 4 of this week's online lecture. Please continue on to part 5.